Okay, question 5E3 for Statistical Rethinking, second edition. So we are meant to write down a multiple regression and evaluate the following claim. And the claim is, neither amount of funding nor size of laboratory is by itself a good predictor of time to PhD degree. But together, these variables are both positively associated with time to degree. Now we are supposed to write down a model definition for what has just been described, and to indicate whether the beta coefficients, or in other words, the relationships between both size of laboratory and what was the other one, and funding, are positive or negative, above 0 or below 0. Okay, so I'm going to tackle this in two parts. Okay, so one, we're going to define the model, and then we're going to think about the beta values, or the relationships between each explanatory variable and time to PhD. Okay, so in question 5E2, we kind of went through the practice of taking a description and writing down a model for it, and so you can see that for a little bit more practice. But here, we first need to define an outcome, and here it's time to PhD, and so I'll call that uppercase T. And we're working with normal linear regression, and so we're going to assume that this equals, or that T is distributed as a normal distribution with mean mu, standard deviation sigma. Okay, but assuming a normal distribution for reasons that I explained in 5E2 is probably not the best distribution to model T with, because a normal distribution allows negative values, but here negative time to a PhD doesn't exactly make sense, and so we may consider a different distribution, but we won't do that until we get into generalized linear models later in the book. Okay. So next we need to regress T on our explanatory variables: funding, capital F, and size of the lab, S. Okay, and so we might use the following model: that mu, the expected time to a PhD, is some intercept, and then the beta coefficients multiplied by the explanatory variables, and sum those up as here. Okay, I'm noticing sometimes I miss the little beta, or the little subscripts on the mu and some of the variables without the I. The I just indexes one instance in the data, so in this case it would be one of the labs or something like that, or one of the students, I guess. So if I miss one of those, then you should know that it's there, that there's not some mystery rule that's taking place. It's an error on my part. Okay, so we might also consider regressing on an interaction term, the interaction between funding and lab size, with another beta coefficient. So altogether, our model without the priors would look either like this, okay, or if we're including an interaction term, we would simply tack that on here at the end. Okay, so next we need to say whether the beta values are going to be positive or negative. And so the first thing that I'm going to do is imagine that we're using this model without an interaction term. Okay, so if you were like me, I had some difficulty understanding this question. Okay, so let me go through what my misunderstanding is and was, and how I resolved it. Okay, so the question is stipulating that neither F nor S, funding or size of lab, are good predictors of time to a PhD, but that their combined relationship is positively associated with time to a PhD. Okay, and now with that information, we are meant to determine whether beta F and beta S, possibly the interaction term, are positive values. Okay, now the reason that I had a little bit of trouble getting through this one is because I'm not entirely sure what it means that these are not good predictors, for one. Okay, so I'm not really sure what good predictor means. Actually, let me come back to that. So the first thing that made this a little bit difficult to comprehend is that when I think about it, I think of both funding and lab size as both helping somebody get through a PhD. So in other words, I would imagine that both of these reduce the amount of time it takes to get to a PhD in general. But we are told that F and S, when combined, have a positive association with T. In other words, they're making it take longer to get through the PhD. And so that just kind of rubs wrong against my intuitions, and that friction in my thinking made it hard to get through the problem. And so what I have done here is I have assumed that time is not time to a PhD, 1 year, 2 year, 3 year, 4 year, but instead I've said the time saved in getting a PhD. And so I'm going to say that the max time to get a PhD is something like 10 years. And so the faster you're getting through it, there is more time between when you finish and 10 years. Okay, so now if funding has a positive association with T, it simply means that funding increases the amount of time you get done, or the amount of time less than 10 years it takes you to get done. I don't know if I've simplified that for you or not, but that's how I'm thinking about it here. Okay, so that was my first problem with this. Next, I'm not entirely sure, or it's not entirely clear from the question, what a poor predictor means, okay? And it's not entirely clear what it means to consider the variables together. So this is how I've resolved it. So I think that a poor predictor, F or S, is one for which the beta coefficient has a credibility interval that more or less straddles 0. And here's the important part, in a single variable regression, right? So only if I'm regressing on one of the variables, either funding or size of the lab, okay? So that means that in this regression and in this regression, oh, I don't have an alpha term there, that should have an alpha term. That means that these beta coefficients in their respective univariate regressions would be poor predictors of mu. And so that would mean that combining them or considering them together would just simply be the multivariate regression. And you notice here again, I'm going to ignore the interaction term, and I'll talk about that at the end. Okay. So if my interpretation is correct, then it raises the question: how can the two explanatory variables apparently have no relationship to T in their univariate regressions, but when they're both put into a multivariate regression, both have a positive association with T? Okay, and one of the answers here, or a possible reason for this, is if F and S are negatively associated. So this would mean that a lab with more funding has fewer students, okay, or a lab with more students has less funding. Now this also violates my intuitions, and this kind of made it hard to grasp what was taking place here. And so instead of absolute funding for a lab, if you take funding to be funding per student, then a negative relationship between F and S kind of makes sense, right? The more students you have, whatever your amount of funding is, less funding you have per student. Now that still might not hold true in the real world, but that's how I'm going to treat it here, just to make sense of the question. Okay. So if F and S are negatively associated, now it starts to make sense, right? So if we're saying that both F and S in reality are helping somebody get through the PhD, okay, they're decreasing the amount of time it takes to get to complete the PhD. In other words, we are increasing the value of T, which is the time saved in getting the PhD. Well then when we're just considering a univariate case, in this case just funding, the effect of S, of lab size, is still there, even though we're not acknowledging it in the data. And so that would mean that as we're getting labs with more funding, we are also, even though we don't know it, selecting or even though our regression wouldn't know it in that case, we are selecting labs with fewer students, right? And so the higher funded labs are going to have fewer students, and therefore that hidden S variable is going to still be exerting its effect even though we haven't acknowledged it. Okay, and so that is going to make it look as though funding has no relationship with mu, okay, or with t. And similarly, if we go the other way around, if we're just acknowledging students, or the size of the lab, F is still there in the data, and it is covertly exerting its effect on mu. It's just that the regression isn't picking it up, but it's still exerting its effect, making it look as though there's no relationship between S and mu. Okay. All right. Now, finally, if we consider an interaction term, now the idea of consider variables together, in my mind, refers specifically to the interaction term, the beta fs and then f times s here. Now, in this case, things get a little bit weird, and so I don't think that an interaction is meant to be considered with this question. But if we have the interaction term, and that is what it means to consider the variables together, well, then the beta f and the beta s can have whatever value. It doesn't matter because considering them together would be referring to the interaction term. But I don't think that's what the question is trying to get at. Okay, that is it for this one.